Hello everyone, welcome back. This is one of the last lecture for the series for my part here, so I hope you treasure it. Okay, I'm also gonna miss you after this. Again, hope the spirit of chemistry and fun stay with you. This is for lifelong learning because chemistry is everything, it's all around us. And what you're learning, we can relate to your family and friends in the future. Today, we are going to speak about part 2 of chemical thermodynamics. As the word suggests, thermodynamics is about energy. From the last part, we talked about entropy and gives-free energy. Today, we talk about equilibrium. So, we relate to theories in the flames and heat. And then what is spontaneity? When I say a reaction is spontaneous, what does it actually mean here? And as you know from the last lecture, that when it gives free energy, the delta G is negative. It is a spontaneous reaction, right? And here you see the Haber-Bosch process, which I explained it. And also in the cell, because this is for the chemistry in biology, how does it affect the potential, right, between the cell here and ions passing through? At the end of this short lecture, you will be able to explain confidently what is K, the big K equilibrium constant, and the laws of mass action. How to write the expression for equilibrium reactions, and the effect of temperature on the equilibrium constant, the Nernst equation, and membrane potential. Now today is a very special day because this morning we just had a Nobel Prize award in chemistry being released. Now, and I met one of them. We had a good news together, and he's a great person, Professor Omayani, in Berkeley. Good times. Now take a look here for this reversible reaction there. How we know it's equilibrium because of this little arrow here. When it's reversible, going two-way, is equilibrium. The delta G is 0, okay, because we say it's equilibrium, and this is the formula. Okay, so what are some of the reactions that you know are equilibrium? Melting, boiling, freezing, sublimation. This phase change, when changing of the metal states, delta G is 0. Okay? And because if we do that, when we make T the temperature, the subject later on, that becomes the melting point, freezing point, things like that. So now, when you have equilibrium, okay, so you can rearrange the equation from previous round, and you make non-Q the subject here, you get the negative delta G naught over RT. Remember this naught here, this the superscript is the standard condition. 1 atm, 25 degrees Celsius. Okay, so we can use the quotient as a form of equilibrium constant. Okay, remember the last lecture? Okay, at least for your syllabus, the Q, big Q is the same as big K. Okay, note this part there. Okay. Again, look at here, and look at here. Right is the same, but because of this assumption, Q equals to K. Got it? Okay. Back to your Haber-Bosch process, very important in the history of mankind, because when we can make a lot of ammonia to make fertilizers, and that changed the world. People no longer starve, there's enough food for people in the world here, and in fact there's a lot of food abundance, right? But it did not came from us innovations in I want to solve starvation, so lack of food. But when we are able to make ammonia, that was the precursor to many chemicals, including ammonium nitrate that was used as a fertilizer. And you know, ammonia can also make urea, can make amino acid, things like that. So for this case, you see that right, where you have the raw materials, the nitrogen gas from the air and the hydrogen gas, right, that we do fractional distillation, so cracking together to form ammonia gas. We use iron as a catalyst, right, at 300 degrees Celsius. Okay. And a very high pressure. You notice that you reach the state equilibrium at this condition. Okay, basically you have a bit of each. You don't have zero amount of the reactant, you don't have zero amount of the product. Okay. So how do we find this? How do we calculate here? This is when delta G is 0. Okay. And you know the expression is always the product concentration to the power of the coefficient, right? Over the reactants concentration to the power of their own coefficient is stated as this. You can relate that. 1 and 2, 3H2 is here. 1, 3. 2 and 3, okay? That's the expression. So if you want to talk about the unit, simple, just do cancellations, right? Power 2, power 4, and you have here. This part we learned before from my lecture on the acid and bases here. When we have the weak acid, you know, because you have the H, dissociated H plus, equilibrium, weak, reversible, incomplete ionization. Ka, big K, acid dissociation constant, product over reactant concentration. Examples of vinegar. Okay, and then it does not depend on the concentration. Okay, this big K only depends on temperature. Okay. So what it means is, right, if I keep the same temperature here, if Ka is constant, this ratio must be the same inside there. Okay. So in this case, when I use a broad example here, you have AA plus BB giving you CC and BB. This is reversible, and then from an acid dissociation point of view, you do not have B, so therefore B is 0. You cancel this term out. This is a reference, okay? Now, because we have both the forward reaction and backward reactions, and every reaction there will be a rate and kinetics there. We learned from me 2 lectures ago. When you have the rate law, you state rate equals to small k, you cannot make it small k, it's the rate constant, right, of the initial reactant to the power, okay, simple. Now, backward reaction, same thing, backward you have the rate, right, the k of the backward multiplied is reactant backward, which is CMD in this case. And then, because you know that for equilibrium reactions, right, it's reversible, it's both way completing. You know that at equilibrium, they have the same rate. The rate of the forward reaction is the same as the backward reaction, so you can equate them together. And when you do a mathematical, operations there, you do a swap, right, from here. You see that the ratio of the forward and the backward rate constant will be the equilibrium constant. A little schematic to show, right, at the start when you have forward very high but with 0, you will come to stability, okay, equilibrium. Notice the axis first. For the amount here, you start with reactant, 0 product, you will equilibrate, but the amount might not be the same, but it will be stable, okay. See the difference here. Rate will become the same at equilibrium, but the amount depends on the equilibrium constant. Big K, small k, both are temperature dependent because of this formula. Okay, just so you know. Which means when we do this rearrangement here, you can do a plot y equals to ms plus c. If this is your y-axis, and one of them becomes the x-axis, you know the gradient tells you something, you know the y-intercept tells you something else. Okay? Y, x. Gradient, you see, gradient, and then y-intercept. Okay. And we can calculate this using experiment, plotting, right? And then you plot t, you plot ln k, right? Reciprocal 1t, straight line. You can find it how to change because r is just your standard ideal gas constant, 8.34. Now we come to the Nernst equations here. We see Nernst think of ions. Electrochemistry. It is an electrical potential between two sides of the membrane. Remember, membrane, a bit about later, membrane two sides here. It's about the selective diffusion of ions across the membrane from a concentration of high to low. As you know, even with this, we have energy barrier. So we talk about channels, right? They can push this ion through selective movement. And virtually, all eukaryotic cell maintains a non-zero transmembrane potential. There will be some charge. Okay. Normally, it's a negative voltage. In the cell here, from negative 40 millivolt to negative 80 millivolt. And because the skin, okay, the cell is so thin, okay, over 10 nanometers, right? So you do a ratio is about 80,000 volt over 1 cm. Now this is a AA battery that dual cell, okay? This video is not sponsored, but I'm just using this example. 1.5 volt. This is battery used probably for 3 months on your clock, right? If you still don't use a clock. 1.5 volts, okay? This is 80 kilovolt. Think of how many battery is it of this battery over a very thin film. Think about that, okay? And we measure the voltage using a potentiometer. But again, this is just schematic for you to see, visualize between the Beckett medium and the cytosol, okay? Between the plasma and membrane there. The membrane potential has two functions there. Remember this. One is to allow the cell to function like a battery. If not, there's no energy to run, okay? Next is to make sure that this neurons can be fired up, in the nerves, okay? The muscle cells is about this energy that got them excited. Why? Because with nerves, transmission of signals. Some people, they don't feel pain, right? Because there's something wrong with this, okay? Either the receptor is malfunctioning or it's not capturing the right proteins, okay? Or somehow the chain gets lost in the communication. And it has a lot of purpose, especially in the brain, because when neurons fires out, that's how memories are encoded, that's how you think, the frontal lobe in the back part here. When you feel frustrations, and the emotions come in, and when you feel happy, dopamine come in. When you have sense of touch, there's oxytocin. The brain matters. So this energy to transport ions across the membrane in ideal solutions. So take a look here. AZ going from zone 1 to zone 2. I use zone 1 to zone 2 because it's like separated by a membrane, okay? So you see, to move from left to right, because high concentration, low concentration, right? Ding, okay? And then ding, okay? You see that? One more time. Ding, ding, okay? So when it moves right, there will be a potential difference, okay? Because these are ions, and ions carry charges and energy. So in this case, I introduced to you this ZF is the energy required to move 1 mole of ions, could be cations and anions, across the electrical potential. Okay? This one you got to know here is the Faraday's constant from, of course, Michael Faraday, the Canadian British scientist. 1 mole of elementary charge E, that represents the number of coulombs. So look at the unit, big C, coulomb per mole. Watch this video if you can here, because you have this nice visualization to acknowledge what happened there. Now the Nernst equations, when you have ions diffusion across the membrane, it generates a electrical potential, zeta. We got zeta potential on both sides. And this diffusion stops when this energy gained from the gradient of concentration, right, is equal to the energy lost. Okay. Basically, it's not enough to climb, and therefore you reach equilibrium. Delta G is 0. And when delta G is 0, we shuffle the terms, because zeta is this. This potential can be switched on and off, right, by opening and closing of the ion channel. So sometimes when, how we have painkillers, right, so we have this drug and then we just kind of use a molecule to kind of choke up the sensor for pain receptor so we don't feel pain. That's it. It's like bluffing the body. So here are some ionic species, right, there's very prominent in the cells there. Intracellular, extracellular, equilibrium potentials here. So naturally these are the concentration in the cell, outside the cell, right, and there's a potential difference. Again, Don't memorize the number, but if you're given a few of them and asked you to compare, I think you can do that for me. So you see here, we got 15 millimolar, remember the big M molarity, mole per dm cube, 145, right? Difference, you have the difference of 60.60 millivolt. This is 17 nanomolar, okay, 2 millimolar. Think of the scale, is it 1,000, okay? Nano and milli. You got it larger. Okay? Same for the following. Here we have pH because we are looking at the concentration of H+, etc. Try to find a relationship. Okay? Top in. Next is the Goldman equation. We kind of substitute from Goldman Hodgkin test, GHK. Now here we talk about the three channels for the ions, sodium, potassium, and chloride. Okay? Again, inside, outside, 1 and 2. So this equation describes the electrical potential across the cell membrane. Okay? What's the equation? Big P stands for the permeability of the membrane for each of the ions. So let's go. This is more physics, okay? But because it's about voltage and electrical charges, we use physics just like a circuit, right? Battery, electrons run in the circuit there, different channels, right? For sodium, potassium, chloride, and calcium, okay? In the cell. Charges move. So equation for the monovalent ions here, we say monovalent means what? Singly charged. Which means we discount calcium because calcium is group 2. Alkaline earth metal. Group 1 only single plus. Group 7, group 1. Because you're doing this, not as a chemistry major, that's the overview, and that's it for you. Again, in summary, today's lecture we cover these equations and briefly talk about the relevance of it in biology in the cells. Need to know this tip of the finger, know when to apply, always unit conversion, and the prefixes. So now you could explain this, and really, that's all. I'll miss you, but I'll see you in class. I'll see you in the result. Take care.